Hi everybody, I hope you guys are all doing well. So I decided to pre-record lectures, that way we don't have issues with lagging. So hopefully I don't have any more issues with lagging. Um, but we are going to be talking about 4.3 derivatives and shapes of graphs. I know I kind of already went over most of this in our Zoom lectures, but because we were having so many technical difficulties, I decided that you know what, why not just start from the beginning and just go over it again. It's a little bit more work, but I think that it's worth it. So we'll just go ahead and get started on this. So basically in 4.3, we're going to be talking about derivatives and shapes of graphs. And the best way to kind of go about this is kind of look at some examples. So in your 125 or your pre-calc class, you might have been able to look at a graph and said, oh, okay, I can tell you what intervals are increasing and decreasing, right? So you could easily look at a graph and go, oh, okay, I noticed that my graph, if I read it from left to right, just like I would read a book, that if I read it from left to right, that it's increasing from here, and then it stops, and then it starts decreasing. So we can look at things like that and identify them. But we are also able to do that with the derivative. So what I want to do today is I just kind of want to go back to 125 for a second, or your pre-calc class, and I want you to pause the video and I want you to tell me the intervals of increasing and decreasing here and the increasing and decreasing here. Obviously this is a video, so I'm going to go ahead and put them on, but you know, it's a good idea to pause the video right now and just write them in just to see where you're at. Always, you know, test yourself to see where you're at. Okay. So hopefully you pause the video and wrote down the intervals of increasing and decreasing. So the interval of increasing and decreasing here is from negative infinity to 1. And that's because if I look at example A, I start increasing here, and then I stop all of a sudden, because right here where I stop at 1, I start to decrease. So, and I don't know how far this is going, but it has an arrow going down. So that means I'm starting from negative infinity, stopping at 1. And so that's where I am increasing. And then I notice that I start to decrease from 1 to 2. Notice that? So that means that my interval of decreasing is going to actually happen from 1 to 2. Then I'm also going to go ahead and start looking where I stopped. So I'm decreasing from 1 to 2, I stop, and then I start increasing here to infinity. So because I'm increasing to infinity, then that means that that goes in my increasing area. So from 2 to infinity. And since we're talking about intervals here from increasing to decreasing, then we need to unionize them. Okay? Perfect. Now go ahead and do the same thing. Hopefully you already did it, but with B. If you haven't already done it, pause the video and go ahead and do it. Okay, so if I'm reading the graph from left to right, I notice that I'm increasing here. Okay, and then something weird happens. Not around, but actually at 2, I have an asymptote. I had a vertical asymptote. So then I have a vertical asymptote, and then I start decreasing. So that tells me that my interval of increasing is from negative infinity to 2. And then I'm decreasing from 2 to infinity. Now, this is where calculus comes in. Now, you learned this all before in your 125 class or your pre-calc class, but I want you to ask yourself, at what point does a graph of a function possibly change from increasing to decreasing? Perfect. So go ahead and maybe pause right now and think about looking at these two graphs. Where am I going from increasing to decreasing? Because it's good to ask yourself that, like, what caused that sudden change in increasing and decreasing? So go ahead and think about that. And also, well, you can put vice versa here, and vice versa. So it's a good question right there. And hopefully now that so go ahead and pause the video. So now that you've paused the video and came back, hopefully you've noticed something, that we stopped increasing right here at a very high point in the graph and at a very low point in the graph here for this one. And remember that in section 4.1, we called these extreme values because they were local maximums and minimums of our graph. But remember now, for example B, that didn't actually happen at any high or low point, but it happened at a really weird spot. So remember that extreme values or critical numbers can also happen when your graph is undefined somewhere. So whenever you have something that's kind of funny in the graph that's not included in the domain, so for example, you have some function and some of its values are excluded from the domain, those can cause change in behavior from increasing to decreasing. So that's why we'll say that the points that the graph changes from increasing to decreasing, those are going to be at our critical points. So yeah, for sure, critical points as we define them in 4.1 were points when our derivative is set equal to 0, but our critical points also can happen from things that are undefined, and that's something you really need to keep in mind when you're looking at graphs in general or your functions in general, okay? Because I can maybe on an exam ask you, hey, find all my critical points, but then I give you something that's funny and it's something undefined, and maybe that point is a critical point, maybe it's not. You need to go ahead and find out, but you want to make sure that you also investigate what's happening at parts that are weird in the graph, so parts that are undefined in your function. So that's super important. I'm not going to stress that enough. Actually, I really like this question here. Could be a really good true and false question. It really shows a lot of understanding for this. So go ahead and just keep that in mind. Okay, so moving on. So what is this? I mean, we just talked about what it has to do with calculus, right? But what calculus gives us is increasing and decreasing tests. So we have what's called an increasing and decreasing test. So let me go ahead and write that in. So increasing / decreasing test. So what does this increasing and decreasing test tell us? So the first thing it tells us is that, one, if our derivative of a function f prime of x is greater than 0 on some interval then f is increasing. On that interval. Perfect. All right. And then 2, it tells us that if our function f prime of x, if our derivative is less than 0 on some interval I, then f is now decreasing. On the interval. So this is how we're going to be able to tell what functions are increasing and what functions are decreasing on that interval. So if the derivative is greater than 0, in some interval, then the function f is increasing, which really makes sense if we go back to our example A and B. So let's just take a look at A. If f prime of x is greater than 0, remember that our derivative is a tangent line of a function. So if I go ahead and zoom in here, right, if I do my little tangent lines on this part of the graph where I know it's increasing, no matter what, notice that my tangent lines are actually just positive. But then when I switch to the part where it's decreasing, my derivative here, or my slope, is now negative. So that actually makes really good sense with everything that's going on right here. So what the increasing and decreasing test is. And now I'm going to pinpoint how you actually use the increasing and decreasing test. We're going to go ahead and just write that out. So let me switch over. So determining intervals of increasing / decreasing. So how do we do this? So we're in calculus. We've been talking a lot about derivatives. So let's go ahead and just calculate the derivative. So that's going to be the first thing we do. We're going to calculate f prime of x. Could also be, let's say, or y prime, or whatever that function is, prime, right? We're just calculating the derivative. That's it. And now our second step is to find the values where f prime of x is equal to 0. So we're going to find the values where f prime of x is equal to 0, or f prime of x does not exist. And so these are also what we call our critical points. And we're then going to plot these on a number line. All right. So basically the first step, calculate your derivative and then set it equal to 0. This is exactly the same way that we found our critical values in 4.1. So really nothing new here. And now the only thing that's different is that we're going to then plot these on a number line. And I'll show you exactly how to do this with an example. And then our third step, and then we also have to account for the critical points, the points where our function is not defined. So remember that a function is differentiable if it's continuous on that point. So if we kind of look back here at this example, this is considered a critical point because we can't take the derivative at 2. It doesn't exist there. There's nothing that we can do there to take a derivative because the function is undefined. I can't plug in the value 2. I don't know what it is. So that's, always keep that in mind. Just because you found where f prime of x is equal to 0 doesn't mean you found all the critical values, right? We need to also address things that are undefined, things where we can't take the derivative because those can cause major issues, and they can change the graph from increasing to decreasing. So always, always, always keep that in mind. Okay, now our third step is the number line. So these are just really steps. Once you do these enough and you do your homework a lot, you'll know exactly what to do them, how to do them over and over again. You won't have to look back at this, but I think it's really good to just write it out. So I will always do that for you. So the number line is now going to be split into intervals. We're going to test a number in each of these intervals. Oh my God, my R's look like these intervals. And determine where f prime of x is less than 0 and where f prime of x is greater than 0 on each interval. And we will indicate with positive or negative. Okay, so that's kind of weird, but just go ahead and write that down. Again, this will make a lot more sense once we jump into an example. So, well, once you have your critical values, we'll draw the real number line, and then now it kind of gets split into intervals. And then from there, we will determine whether, or indicate whether the derivative in that interval is positive or negative, just like where the splits are happening. So we'll go ahead and just go over that. And now our final step is step 4, is then f is increasing on intervals denoted by that positive value. And then take a wild guess here. It's decreasing with the negative ones. Perfect. So this is like your steps to determining whether a function is increasing or decreasing. Okay, so we've outlined the steps of how to find intervals of where something is increasing and decreasing. Let's go ahead and now do an example. So our example here is find where the function, and let me rewrite this where, it's a little out of hand where. Find where the function f of x is equal to 2x cubed plus 3x squared minus 72x plus 12 is increasing and where it's decreasing. So what I want to do now is I want to kind of follow along the steps that we kind of outlined here, just so that we can see how they come into play. So our first step here is to calculate f prime of x. So let's go ahead and do that. So let's do our first step and calculate f prime of x. Okay, so go ahead and pause the video for a second so that you can go ahead and just calculate f prime of x, and then we'll go ahead and check our answer together. So hopefully you got f prime of x is equal to 6x squared plus 6x minus 72. So that's our derivative. And so our second step now is to find our critical numbers. And so in order to find our critical numbers, we want to set the derivative equal to 0. So if you notice that you can do some simplification here and factor, go ahead and do so. But if not, you will be able to see it in the second step. So go ahead and find your critical numbers. So find where f prime of x is equal to 0, and we'll call these our critical numbers. And this is where we're going to do some investigation, right? And so when we do that, we'll just set 6x squared plus 6x minus 72, and we'll set that equal to 0, because that's how we find our critical numbers. We learned how to do that in 4.1. And so in order to do that, I noticed that I have a regular quadratic. So I'm gonna have you find out where x is equal to 0. So go ahead and pause the video right now and see if you can find those values. And then I'll do them right now, obviously, but pause the video, try them yourself. Hopefully you can get to that, okay? And so I can factor out a 6. If I factor out a 6, I get x squared plus x minus 12 is equal to 0. And then I can go ahead and factor that. I get 6 times x plus 4, x minus 3, and set that equal to 0. And now I can use zero product property to find my x values. And so hopefully you got your critical numbers to be -4 and +3. So these are our critical numbers. Cool, so we already did 2 of those steps. And now the step that's kind of new is that we're gonna do this kind of testing that you probably haven't seen before. I mean, you have, because I talked about this on our Zoom lecture, but I'm redoing the lecture because, yeah. Okay, so now for our third step, it's to draw that line. So let's go ahead and just draw that line. So it says, that third step says, please draw a number line. And this number line is just your real line. And we'll put in our critical numbers that we found, which is -4 and 3. So, oops, I'm using eraser. So we have -4 and 3. Okay. Now, usually I would ask you to be careful and make sure nothing is undefined. So it's a good idea to kind of look back at our function and go, okay, we were dealing with a polynomial here. There's no issues here. Everything's okay. So my domain is all real numbers. So I don't need to include anything else in this number line. If I had something that was undefined, then I would possibly include that there. But for now, we don't need to do that. Okay. So now it says, okay, the number line is now split into intervals. Test a number in each of these intervals and determine where f prime of x is greater than 0, less than 0, and when f prime of x is greater than 0. So they want to know, when is that derivative greater than 0 and when is it less than 0? And so the best way to do that is we're going to test points in our derivative. So what we're going to do here is we're going to find a value, let me do this in red, for f prime on this side that is equal to 0. It just lagged a little, I'm sorry. Okay, so we're finding the point here where f prime is not equal to 0. We're going to find where we're going to test a number after 4 in this little area here. And we're going to find out, is that number positive or is that number negative? That's what we want to know. That's what we want to investigate. And then we're going to test a number between -4 and 3, and then we're going to test another number after 3. Okay? And we will always do this in the derivative. So we're testing values here. So anything after -4, we can say, I would just choose the easier numbers, so the smaller the better. And I usually tend to use whole numbers just to make my life easier. And so let me just test -5. So if I test -5 here, plug it into my calculator, remember I'm plugging this value into our derivative, so we're actually plugging it in. You can plug it into the simplified version or the other version, that's fine, it doesn't really matter. We'll just plug in -5 into there. So go ahead and do that on your calculator, and then hopefully you got something like 48. Then we're going to test a number between -4 and 3. And whenever I can test 0, I always test 0. So let's go ahead and test 0. If we test 0, we notice that our value is actually just this end piece, because then 0, 0 over here. And so you're just left with that -72. And then on this side here, what we want to do is now test a number after 3. So a number after 3, that's like 4. And then what happened? That's 4. And if you calculate that, you'll hopefully get 48 again. Okay, so now that we've calculated those values, I don't really care what the value actually is. So I don't really care for the fact that it was 48, -72, or 48 again. So I did that just so we can see what's happening here. What I care about, and what you should always care about, is the sign on that function. We care whether this value here is positive or negative. And so that's how we're going to denote those values on our number line. So here, this value 48, that's positive, so we'll go ahead and put a plus sign here. Here, this value here is negative, so we'll put a negative sign there, and here positive again. Super simple, super easy. So at the end of the day, if you can tell that when you put a function in the interval somewhere around this value, and you know for sure it's going to be negative, then you don't need to even use your calculator. Just say, hey, it's going to be negative. If you can see that ahead of time, because what I care about and what you should care about is what's happening to my derivative. Is it positive, negative? Is it increasing, or is it decreasing? And so you can put plus, minus, plus, but a habit that I like to do, and this is really helpful for what we're going to do next, is I like to denote that by an up arrow to show me that I am increasing, and then down arrow by decreasing, and then another up arrow again. Okay, so now let's do the fourth step right over here. Okay, because for the fourth step, it says if f is increasing, f is going to be increasing on intervals that's positive and increasing that's negative. So at the end of the day, this question just simply asked us, is this function increasing or decreasing, and where is it increasing and decreasing? So let's now just write down our answer, increasing. Now we can easily see where it's increasing. It's increasing here, and it's increasing here. So it's going to be increasing from -infinity to -4, sorry, union with 3. Let me actually move over to let me move this a little bit over so I don't get all squished. Union 3 to infinity. And then I decrease in that little middle area between -4 and 3. Perfect. And so that's our answer. It's not too bad. And what's really awesome about this is that this is all stuff that you've done before. You already knew how to calculate the derivative. You've been knowing how to calculate the derivative. And we learned how, and then you set that derivative equal to 0. That's easy. That's just solving an equation now. And now the one thing you did learn is that you need to test the points. And the one thing that you should take away from this is that when you test points, you always test on your derivative, because testing on the derivative tells you if it's increasing or decreasing and if it's positive or negative. So at the end of the day, you care what the value, the sign on that value is. Is it positive or is it negative?